Thanks for the invitation to present today. My name is Patrick Law. I'm the Research Reproducibility Coordinator in our school. I'm this presentation today, so if it's any good, I'll put it online later. If anyone's watching this in the future, I'm in front of our school's top research students, helping educate them on this topic. So the overall plan is explain what is this thing, reproducibility, and its related concept, replicability. Talk about why we should care about it, and then sort of how to do it. There's different stages of how much you want to do. So let's see if this is relevant to anyone in the room first. Put your hand up if your current or future research will use Excel, MATLAB, Mathematica, Python, R, SAS, data, or any data set or any programming language. You're not putting your hand up? Okay. We should everyone. Okay. We got everybody. This is relevant to all of you. Good. Okay, another question. Well, I've got you. Now I'm sure you're awake. Which one of these do you trust? Right. So your two options are ChatGPT, and the second one is a research paper. Okay. You have to pick one or the other. First off, ChatGPT. Hands up for people who would trust ChatGPT. Nobody? Okay. The research paper. Who trusts research papers then? Young doesn't trust anyone. Okay. Okay. So we can tell who is the senior one here. So these are actually, I picked two famous examples here actually. The left is famously the GPT can't tell you how many times the letter R appears in the word strawberry. It gets totally confused. So this conversation, I tested this on Sunday. So that's actually my conversation from just a few days ago. How many R's are there in strawberry? There's 2. Oh, wow, that's surprising. And it says, yeah, it's easy to overlook, right? There they are. Are you confident? Yeah, I'm quite confident. So obviously ChatGPT is well known for lying and hallucinating confidently, right? But research papers, we hope we can trust them to be quality. And this one in particular is from The Lancet, which is a medical journal, the top most prestigious medical journal, like following from the previous talk. But it took me a long time to find this screenshot of this specific paper, because that's what it looks like nowadays, actually. This is a famous case of a paper that got retracted 12 years after it was published in the Lancet due to fraud. This is the original paper that started the whole vaccines cause autism fake news. It was caused by the bad research practices, that the people were being funded by the research wasn't being funded in the right way, and this spawned, nowadays people believing this untrue facts have led to lower vaccination rates, more outbreaks of measles, when we shouldn't even have that anymore, right? Okay, so here I'm saying, okay, there's an example of a research paper where it wasn't true, right? What they had in it, but that was fraud, right? Surely that's quite uncommon in the scheme of things, and you'd be right. However, here's another paper that wasn't fraud. And does anyone see anything a bit weird with the introduction of this paper? If you can't read it, it starts off with the introduction. Certainly, here is a possible introduction for your topic. And then goes on, right? This also got retracted because this person had obviously just got ChatGPT to write the vast majority of this paper. Okay? So even without particular malice, there's laziness as well we have to compete with in assessing whether a research paper is even making valuable points or not. And to really drive this home, why would you not trust ChatGPT specifically? Let's say because of the process. We put things into this AI, it's a black box, and then we just get some output, and we just have to trust the output. We don't see the data it was trained on. We can't step through the thought process that the AI went through. We can't verify that it made any mistakes in its steps. You just have to trust it, and that's not good enough. for us. That's not good enough. With research papers, it's actually pretty much just as bad for most of them. Right? With reproducible research, which is what our topic is today, you could in principle do all these things. You could see the data that was used to make the claim, step through their code, their process, and verify it step by step if it's reproducible. So we're dealing with papers, whether they're making claims that are true or not true, and how do we trust them? So if we didn't trust the paper, how would you check it? There are two very different ways that you can go about assessing a paper's quality. One is to reproduce it, one is to replicate it. So we'll be talking about reproducing today, reproducing a paper, and that's basically like auditing a paper, taking the paper, its original code, its original data set, rerunning the same, say, statistical analyses, and trying to produce the same statistics, tables, and figures that were in the paper. Right? We expect to get no changes. That's reproducing the paper. And then in the process of stepping through, we can verify as well whether everything is how we hope it to be. Replicating is a totally different thing where we take, and it's more common in other fields like medicine and physical sciences, where you take the idea of another paper and then you take like a description of the experiment they did, and then you go do the whole experiment again. You redo the whole thing again, go and collect new data, analyze it again, and then you hope that the main results kind of line up with what the main claim was in the first paper, right? And this is fundamental to just the scientific method, right? That we make some claims and other people can also replicate those results. But unfortunately, I won't talk about replication much, but I'll give you one example here. And it's a 1-minute clip from this highly recommended video that I'll have linked to here. I'll give you a minute clip from it from this video now, and a bit later a slightly longer clip. So this is talking about the replication crisis. Let's see if we can, hopefully we can hear this properly.
As editor-in-chief of The Lancet, which is the most prestigious medical journal in the world, I think, or at least it used to be until this quote came out. So Horton was at a closed-door meeting of heads of granting agencies and journals in the UK back in 2015. And after that meeting, he couldn't share any exact quotes because it was closed door, but he wrote an editorial in The Lancet about this meeting and lots of the shocking things that had been reported on. So this is the quote. If you'll indulge me, I'll read it. The case against science is straightforward. Much of the scientific literature may simply be untrue, afflicted by studies with small sample sizes, tiny effects, invalid exploratory analyses, and flagrant conflicts of interest, together with an obsession for pursuing fashionable trends of dubious importance. Science has taken a turn towards darkness. Yeah. The only thing I disagree with here is the end. I think we've been in darkness for a long time. I'm going to make that argument like this.
So that was the person who's in charge of The Lancet, the top medical journal, saying, okay, half of this stuff in my field is just wrong. I publish all these papers, half of them are probably just false. And there was other famous cases. So a biotech company in Germany about 10 years ago took like hundreds of cancer studies that had been published and tried to replicate a whole bunch of those experiments to see how many of them they could get the same evidence of their claim as were in the original paper. Does anyone want to guess what fraction of them could be replicated? 40? Anyone else want to guess? 10%? Their conclusion was about 25% they could replicate. So which is to think of how much time and effort was wasted in trying to build on those 75% that are just a waste of time, basically. How much money, time, and effort. Okay, and I think this is near the end of my introduction slide. So this is from These guys that do wavelet research, a quote from the 90s on reproducible research. So it goes, researchers in the fields that do computational experiments can't reproduce their own work. Students in those fields can't explain to their advisors the difficulties they're having, and researchers in those fields can't reproduce the work of others. To people who have only worked in such fields, this probably seems to be just the way things are, so much so that this state of affairs is unremarkable. In the field of wavelets, where we see a mixture of researchers from several disciplines, it's easier to take a broader perspective and see the situation as it really is, a scandal. So this is a quote from 1995, and things haven't really changed since then. And I know many of you are basically mathematicians inside the business school. I mean, I came myself from in this direction. I know you might be thinking, oh, but I write proofs. I know my things are totally true. I do want to say, though, that you're not totally safe from this concern of having other people trust your results, right? You need if you write a paper, you need others to believe your results to be true as a prerequisite for anything useful to happen, for them to cite you, for them to use your methods to change policy, right? And here's an example I found of this big team of researchers in pure mathematics who, I think in the 90s, oh, sorry, got it here. In 1980, they were saying this long proof had been completed. We proved this thing, the finite simple groups theorem, but it failed to attract much attention. Even within the subject, many people were skeptical. The reason why, the proof took over 10,000 pages, was spread across 500 or so journal articles, and it took 100 different authors, and this was spread over a span of 100 years of work almost, right? Just to prove this one theorem. So complicated. And it turns out the skeptics were later proved right. Actually, there were problems with this huge proof, and then it took them another 20 years to plug the gaps in that were pulled up, right? So even if you're doing pure mathematics, you still need to be able to convince yourself that you're doing something that's correct, and still need to convince others what you did was correct. Okay, so moving on to
I think it's quite different because in math field, the retraction is less frequent than medical science or some other field.
Yeah, well, in terms of, I did hear, for example, in terms of academic fraud, medical sciences is way higher rates of fraud than any other one. So that is
depending on whether they do this intentionally or not.
Yeah. Well, that fraud, I think even in medical science, it's super rare, but sloppiness, errors, typos, I think everyone makes these mistakes. We're all human, right? So I think, in mathematics, there's still typos around. Okay, let's get a definition. Reproducible research. A published data analysis is reproducible if the analytic data sets and the computer code used to create the data analysis are made available to others for independent study and analysis. So what does it mean? It really boils down to that you do your research and you make some claims and you have evidence to support the claims. Right? You have evidence and you are able to provide that evidence to other people. That's the fundamental nature of reproducible research. So these authors from 2018 made a list of reasons why you should bother making your research reproducible. The first two are about verification, right? So firstly, to verify that your own work is correct, right? Because if you think about you're going to write some research, publish it in a paper, then you're going to go to conferences and promote your work, potentially. You need to be sure yourself that your own work is correct before you can go do this. And if you're starting your honors thesis or PhD and you're heavily basing your work off, say, one paper, which is common, you also want to know that that work is correct, right? You don't want to waste your time on something that has a fundamental error in it. Or more abstract reasons why you would do this, to increase your own productivity, actually. So some of the practices that you pick up for reproducible research will just make you more productive in general. And enables your work to be extended by others, It lets your work survive technology evolution. So that means that if you use some computing system today, maybe it doesn't exist in 10 years, but if you set it up correctly, you can sort of work backwards to still use your old code and analysis. And lastly, if you put your research code out into the world as open source, then the open source community can step up and help solve any potential bugs or make extensions, and you can spread the work amongst many people. Okay, so on the verification point, a few more quotes in this section. So this person argues that the basic function of a paper is to both announce some result and convince the reader that the result is correct. However, some other researcher claims that the majority of published research findings are false due to many reasons. In most fields, peer reviews serve to evaluate whether the work as described is sound, significant, and interesting. But with rare exceptions, reviewers do not have the time, inclination, or skills to perform or verify the work described in the paper, particularly if it requires unusual, expensive methods and facilities. And that's all true, but it's a bit sad because a lot of what we're doing is kind of computational activity. It is in theory reproducible given the same code and input and a compatible machine. So it should be possible to reproduce it. Another way to look at reproducibility as part of your research is just thinking about your communication strategy. How do you think your research is going to spread out into the world, basically? And another quote I really like here is, an article about computational science in a scientific publication is not the scholarship itself. It is merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. So if your work falls into this category, then yeah, of course the paper itself is not super meaningful in a sense. The way I see it though is that in my, say, communication strategies, I take my work to a conference, try to present it, get people interested in the thing that I did, right? Get them excited about my paper. If they're excited, then they might go off and read the thing. I read the research paper, and we hope that they're convinced by your results in the paper. They find it convincing and useful. And then the last part, which is the reproducibility part, you also have your code and your data available so that when they've read your paper, they want to do something with it, they want to build on it, apply it. They can trust what you've done because they've got the code, they can check it. And if they really are trying to build on it, they need to understand every low-level detail. And that's what the code is there. The code is a description of all the low-level details in your research. And who should be worrying about this? Right? So we've got Roger Pung and Hicks from 2021. In much of the early literature on reproducible research, the focus is on, quote, computationally intensive research because of complex computer stuff, which is considered more impenetrable than other research. Fast forward 30 years, and computing and scientific research is ubiquitous. It's no longer the domain of niche geophysicists or mathematical statisticians using obscure computer packages. Now, all scientific research involves the use of powerful computers for collection, data analysis, or both. And the statistical techniques we're using are getting more and more complicated over time. So the conclusion is we are all computational scientists now. Thus, the concept of reproducibility is relevant to all scientists. And if you haven't been convinced by all these different reasons why we should care about this, why we should do it, let's say who benefits the most from having your research be reproducible? And I really love this quote. It takes some time to organize your research to be reproducible. We found that although the effort seems to be directed to helping other people stand on your shoulders, the principal beneficiary is generally the author herself. This is because time turns each one of us into another person. And by making the effort to communicate with strangers, we help ourselves to communicate with our future selves. So this is, I've definitely felt this many times. Looking back at my papers from the start of my PhD, it is as if someone else wrote them. I don't know what I did. And the code that's like that as well. And when I was doing my software engineering degree, I remember a lecturer asked me, asked the whole class to think about how many of you think that the code you write in your career will still be in use 100 years later? And I kind of have the same question for you to think about as well. How many of you think that the research you write will be used in 100 years' time? So maybe think about when you're going through your reference lists, what's the oldest paper that you cited? Maybe you cited, if you're more mathematical, something from the 1930s or something like that. That's paper that's had a very long impact. But even if you didn't cite something from 100 years ago, you cited something from 20 years ago, which cited something else from 20 years before that, and from 20 years before that. So there's a very long life of research that we need to think about. And the way that it's if you've never really thought about it before, I'm just trying to run the code on the same data. That should be easy. We hope it should be super simple. In principle, they should be easy to reproduce, especially when compared to physical experiments, right? So we're not going out and injecting people with new drugs or painting up surface or something. We're just running a computer program. Assuming that a computer is a deterministic machine, simply applying the same program to the same inputs on an equivalent architecture should give us equivalent results. But in practice, the complexity of today's software and hardware makes it surprisingly difficult to do this. And this is actually a fundamental problem that people who are trained in software development have as well, right? We actually have a lot of the same problems. So if people are trying to want to read that one, I can zoom in for you. 20 replies by programmers when their code doesn't work. And the very last one is the most prevalent. It worked on my machine. It worked on my machine, my code. So I don't know why it doesn't work on your machine. And this is like one of the number one things that you're taught as a software developer, how to get around that bug. Right? That's one fundamental bug that that software people have, and they have solutions for, that researchers have as well. Software people also have very common problems of I have something, I'm adding things to it over time. I need to keep track of all the different versions. So version control in the software world is the solved problem. Continuous integration is this idea of multiple people working on the same project, and you're trying to keep track of everyone's inputs and weave them together in a cohesive way. A solved problem for software people. And even code reviews. I wanted to tell you a little story about that one. So my very brief experience as because I studied as a software engineer and mathematician, and I had only one very brief experience in industry as an engineer, and that was down here at Google as a software engineering intern for the summer in 2014 or something like that. And when I was there, I was only working on some kind of toy project as an intern. But even at such a low-level person, they would not let me save my code before another engineer read every single line and approved of that code. Every single line that I wrote had to be read, approved, and go through like a peer review process in itself just to save the code. So that was what they called code reviews. And if you contrast that to research code, where, I mean, a bunch of you guys will be writing it basically, when I don't think you're trained software engineers, I don't think your supervisors will read the code. Most of the code you write, nobody will read, right? So if you think about that, it's kind of sad, right? Because the useless stuff I was doing at Google, right, helping them sell advertising to people, gets thoroughly reviewed. Whereas here at a university, where trying to cure cancer and do big important things, oh, well, any old code will do that. No one checks it. Doesn't matter. So long as it doesn't crash, it's probably good enough, right? Okay, so that's the problem, why we should be thinking about it. Now, I've split up into two different levels, how much we should do to solve this problem, because it's not like a 1 or 0 thing. It's reproducible or it's not. There's kind of different steps. I've broken it up into different levels. These are 1. Can you reproduce your own results? So if that is, you've taken something to your supervisors. You said, here's my draft of something. They're like, oh, okay. How did you get this statistic? How did you get that? If you can't go back and get the same number again, you've already made something's fundamentally wrong there. That's the base level. You need to be able to reproduce your own results a second time. Level 2 is being able to do that same thing, but on a different computer, basically, which is harder than it sounds, but you need to be able to just internally, this is not even sharing with other people, just you be able to do the same thing twice and be able to do it on a different computer. And then level 3 is sort of what I'd call the bare minimum for reproducibility. That is, what can others read and understand your code? I'll go through all of these in detail. Level 4 is, which is really what we should be aiming for, can others run your code and get the same results? Right? That's our definition for reproducibility. And lastly, the one that's quite hard but very, very useful is, can others adapt your code to new data, new situations, do something valuable with it? Okay, and before all of that, there's, oh yes?
Are you referring to like reproducibility and the
actual code? The whole thing is actual code. Yeah. Yeah. So level 5, I'm basically talking about making software packages, statistical packages at that point. Okay, so there's also a level 0 before that, which is just not using Excel at all in your thing. So I've got an example here, and I really can't explain it better than Richard, so I'm just going to leave this run for about two and a half minutes. So very interesting though.
Sure, that's what I'm going to talk about. Let me give you specific examples. Indulge me here. So these are famous examples. Apologies if you've heard them before. Reached that phase of my life where I'm telling the same story over and over again. I need to do better about that. But so here's this example from economics. I think Harvard economists Reinhardt and Rogoff in 2010 published this paper. It was a preprint at the time, Growth in a Time of Debt. And this came out where there was this recession in 2008, right? And there were a bunch of international debates about public spending in order to stimulate the economy and so on. And this paper made the argument based upon this single graph that public debt is bad for growth, that there's a negative correlation between the debt to GDP ratio, which is on the horizontal axis, and the percent growth in GDP. And so this is the whole paper, basically, is this graph. And this paper actually had a big impact in parliaments and in the U.S. Congress. In the U.S. Congress, it was actually waived on the floor of the U.S. Congress in a debate about public spending. Anyway, it turns out the data were wrong. The analysis was just wrong. It was just an Excel error. And here's Thomas Herndon pointing at the error in the Excel spreadsheet. These are the unsung heroes of science, the people who actually look at the detailed analysis and figure out how the results work. And in this case, Thomas saw that there was just a formula error, and they had failed to include some countries that went against that trend. Unless you actually drug the formula down all the way in the Excel sheet, the result vanished. This is the actual spreadsheet. You can see that if you know how Excel works, first of all, apologies. I'm sorry that life has done that to you, that you have to use Excel. It's a terrible tool, but that blue bounding box that you see is where the formula input range is, and you see that they just excluded some countries down below, and those go against the trend. So it's an error, yeah. And but lots of policy was made on the basis of this paper before the error was discovered. This is sloth, right? This was not an intentional deception either, because the authors provided the spreadsheet. They weren't trying to cover anything up. They wanted to get this right. Right? This is the kind of thing that arises from a sloppy way of working, using a tool like Excel, which is not designed for scientific analysis and provides no or say very few tools for quality control and inspection. It's designed to be convenient and visual, and that is exactly what you don't want in a profession like this.
Yeah, so, so it's sad to think that European economies went through austerity measures just because some Harvard professor who published in a very well-reputed journal didn't move their mouse down a few more millimeters right when they were dragging the formula. And Europe went through austerity because of that mistake. Yeah. Okay. Well, I'll show some more Excel problems in a moment, but let's move on to what I'm calling level 1, reproducing your own results. So first, these are the most basic things that we can start off with, which is, do you still have the original data that you used to make your research? Do you still have the code that you used? This is so fundamental and basic that many people don't do this. Right? So firstly, do you have any data related to the project left around? So this is about data storage. But on top of that, do you really have the original data, right, before you made any modifications? So let's say, here's an example here. Here's a data set. This happened to me, actually. One of the people in our school, Jonathan Zavei, paid for some very expensive data about house prices in every suburb in Australia over time. And it's a very large notebook. So you get this alert. Okay, I ignore it, whatever. And because it's all private data, I've filled in all the blanks with uniform garbage here. So all those numbers are noise. But let's say that we were doing our analysis. We thought, oh, okay, this one is obviously an outlier, this row. So let's just delete that row here. That was an outlier. This number, they probably typed that in wrong. Probably was meant to be 1.4, and maybe this was in listed in American dollars, but we should be putting it in Australian dollars, for example. So we do the thing where we replace that, where we update it, right? Oh, we've fixed that column now. So now it's in Australian dollars. We save that, close it. Later, when we come back, we have absolutely no way to see what the hell happened, right? What did we even change last time we were around here poking around, editing these things? Excel has no way to tell us what you changed. You should be leaving the data as completely raw data, never changing that, and then inside your statistical software do these things, do rescaling, pre-processing, outlier changes like that. And in particular, I picked this data set because if you notice, actually, this was I made a copy of the data set before I did that change, 420 megabytes. And after I hit save there, it's down to 120 megabytes. Does anyone know why this is the case? Exactly. So you've had this issue before, right? Excel just doesn't like big files. So the original file had a 2.8 million rows in it, but Excel just can't handle that. So it silently deleted everything after the 1 millionth row that it just couldn't handle. So all the expensive data we just bought, it's kaput, gone, because Excel silently deleted it. So there's so many problems here, not just with Excel, but also with modifying your raw data at all. Okay, on the code itself, it's often, if you read papers enough, you'll see this thing in the paper that the authors are happy to provide the code upon request, right? And you might think that that's good, right? That's better than not providing the code. But, as soon as they drop their computer into a pond or something, then kaput, there goes the code forever, most likely. Or people have tried this, they do experiments where they go through a whole bunch of papers in a field and then try to ask the authors, okay, trying to reproduce your results. Can you send your data in code? And it's like 30% of them can even find the data in code that they had and and they're willing to send it to you. So the solution here is to have some kind of plan for your data. You should be doing this for anything important, right? Have short-term backups, say Dropbox, have long-term archives, and the standard one there is GitHub. Running your code twice. Now, this is important because sometimes models that are actually randomized inside modern statistical code, right? If you're doing some kind of random sampling or bootstrap, you want to set the seed so that every time you make these random choices, you're making the same random choices. Or if you're doing some kind of machine learning thing, normally your model gets randomly initialized at the beginning and then you train it. And the model you end up with is different based on how you randomly initialized it. So make sure to set the seed inside your code for your random number generator and check that it worked. Actually run your code twice and look at the difference before and after to learn how to save the relevant tables and plots and results to a file so it's easier to spot when things change rather than just relying on sort of manually copy pasting things from your R terminal. So there's a quote here. Ideally, a scientific workflow will be fully deterministic and the results will be always identical. However, there's many sources of non-determinism that contribute to the results being different. And the degree to which small sources of non-determinism affect an entire experiment is important to consider. And I'd add more to that. If there's one bug in your entire research code, you could probably throw away the whole paper, frankly. If you can't, you really need, it's the kind of thing, everything needs to be right for you to be able to believe in the results. Another one is like, say, your supervisor points to some part of your draft and say, okay, how did you get this number, right? Or how did you get this statistic? Oh, yeah, there's a question.
If I put those on packages,
We're coming to that in a bit too, actually. What happens if I rerun my code a bit later in time, then the environments are a bit different. So there are tools for that. Good question, good thinking. So this one's a bit of a recommendation. So say that what you would normally do when you're writing your research paper, your thesis, right? You have your R terminal, your Python, whatever, and then it's printing out results and you copy paste them into like an overleaf document, something like that. That's okay, but then later on, say you change something in your code, you change the data a little bit, then basically every single part of your overleaf document needs updating, and it's not automatically linked, right? There are systems like Quarto or R Markdown where you build the code right into the document, right? So every time you render your Quarto or your R Markdown, it generates a paper with the fresh results, right? Because it's actually running the code each time. And you never have this problem of something in your paper being out of date because you changed something and you forgot to copy it over. Level 2 was being able to run your own code, but on a slightly different machine. And so one thing that I see, my students send me code and like, I'll just run this code, and then it crashes immediately, right? It says, okay, their R code relied on a bunch of packages to be installed already, and they didn't tell me what they were, and sometimes it's most annoying when they have this kind of thing right at the bottom of a very long scripted code. So I've done heaps of hours of processing, then crash, you didn't install such and such, and all that's wasted. So this is one thing. You need to be able to have some way of recording what packages were required and the specific versions as well, because they change over time. One of the first things I see with students send me R code, the first line is set working directory to C users : Tom and Jerry, whatever documents, right, for their specific computer, right? But I don't have a Tom and Jerry file on my computer. This line crashes, right? Every time there's a specific hard-coded path like this, And then there's usually, when there's one, there's usually many of them. You have to go in every single one, delete, change it, update. That's time consuming and frustrating. Whereas if you learn how to use relative paths instead, you can say, okay, given that if I load the script from the current working directory, I know there will be a data directory beside that. And inside that is my dataset.csv. And that will run on my computer, on someone else's computer. And that's way simpler, especially if you're just working yourself. You're just swapping between maybe your work computer, your home computer. You can solve a problem there yourself. And another thing that's handy is when you're testing this yourself, okay, does my code run? Can I make it run on another machine? Is to test it on a different operating system at the same time. So maybe you have Windows computer in the office upstairs, you have a Mac at home, you'll find lots of things crash when you try to move from one to the other. And if you fix that now, you can imagine that's reducing the pain for someone in the future who doesn't have the same exact system as you. I'll skip over those examples. Okay, so we're up to level 3 out of the 5, sharing code with others. Now this one, the question you're asking yourself here is your code and data available online? As I said, some people try this thing where they say, okay, my code is available, except that someone has to just email me. Then I have to be in a good mood. I have to be able to find that stuff and send it back to them. There's so many points of failure there, right? And remember, the whole point here is you actually want people to look at your code. You want them to be excited about your research and do something with it. So you shouldn't make it hard for them, right? So the standard thing here, and it might be different for different disciplines, but most of them is to just put the code on GitHub, make a GitHub repository, and then it's easy to find as well. So even if it's on GitHub, okay, does anyone know where to find it on GitHub? It's a big website. Make sure in your paper that you're writing, just put the link in there, right? Put your Dropbox, your GitHub link. I have seen Dropbox link, but that's a bit fragile. Okay, and as preparation for this lecture, I went and created a bunch of GitHub setup videos for you to look through in the future. And this goes through the steps of how do you make a GitHub account, which is just as easy as making a Facebook account. It's not that complicated. The easiest way to add files to GitHub, again, that's super basic. It's just drag and drop. That's it. But I mean, it looks a little intimidating the first time, but once you've seen this, you'll see it's very straightforward. And then if you want to use Git and GitHub for version control as well, and to do a proper, like a very traditional kind of workflow, then you need to learn a few more things. And that's what the other videos are for. Yeah. Okay, now level 3 was, can other people read your code and can they understand it? Right. And this is actually where it gets a bit tricky. I've got one of my favorite quotes here from a computer scientist. Any fool can write code that a computer can understand. Good programmers write code that humans can understand. So this is the fundamental, where we're getting to things that are fundamentally difficult for researchers and for professional software developers as well. And I wanted to tell you another thing that we pick up in ComSci. It's called the bus number. The bus number. So that is looking at a project. Say you're in a startup, you're writing some code. How many people in your team would it take to be hit by a bus before the code is totally unusable, that no one is left that understands the code, right? So it's a pretty depressing way to put it, but the idea is, right, if you have some fundamentally important thing, many people should be able to understand what's going on. They should be relying on one person to be able to run that code. And let me tell you, for your research projects, for your honors thesis, for your PhD thesis, the bus number is 1. You are the only one that understands this stuff. No one, you might think, okay, my supervisors could pick this up. No, they can't. They wouldn't. You're already the expert in this niche field more than your supervisors, right? So writing your code in a way that is understandable to others helps alleviate this problem that If you step away from this project, then the project's dead forever, basically. That's the problem. And I mean, say you're still finishing your honors, you're still finishing your PhD. Say you do want your help from a supervisor, co-author, some other expert that's very proficient in this field. Imagine the two scenarios, right? You give them a small, clean, well-documented bit of research code and say, please help me, I'm having this trouble. Or you give them some 10,000 lines garbage of spaghetti code with no comments or structure, no explanation of what's going on. And you say, please help me. What are they going to say, honestly? In theory as well, I mean, when you submit your paper later, your reviewer needs to understand the method as well, although almost none of them will bother to read through the code, but I'll be honest about that. So in theory, they should, if they needed to, but very unlikely. Okay, writing clear code. Okay, first thing, is it written in English? So if the paper is written in English, the code should be written in English as well. There's no reason it should be in a different language. I mean, if you're writing a paper for some French statistical thing, and you're writing the paper in French, yeah, you can put the code in French too, right? They're the same. That's the target audience. But where most of us, at least, we work in the world of the English language academia, the code should be in English as well. Are there comments in the code? Now, this actually, I think, gets a bit emphasized too much when people talk about good code. It's when there actually shouldn't be that many comments in your code, and the code comments should talk about why something is happening or why not. It shouldn't talk about what is happening or how it's happening, because that's actually the code itself is the how, right? I've seen people write comments to read in the data set, and then the next line is read dataset.csv, right? That comment was totally pointless. I could just read that code. And try to think about how you name things inside your code. And to be honest, this is hard even for stuff for developers. And so this is a link to a 1-hour keynote conference at a large C++ talk. 1-hour keynote talk at a conference, which is all about just naming variables, naming files, and so on. And another quote for you here. There are only 2 hard programs in computer science: cache invalidation, naming things, and off-by-1 errors. So programmers have a bit of a difficulty to name things, and I like this part of this slide from Kate Gregory here. Naming requires empathy, because you need to think about how other people view your code, empathize with how confusing they'll see it. And I'll add to that as well. Research reproducibility requires empathy. You need to be able to empathize with a total stranger who hasn't spent as much of their life as you have in your own niche, in your own code base. Try to feel how frustrating and confused they would be coming into this for the first time. So this is something, as I said, professional coders are taught, but I mean, still find difficult. But at least we have the mindset that, I mean, code is written once, but read many times. So that's one mindset to try to embody in your own code. And here we're going back to the Hung and Hicks paper. The primary purpose of sharing code is to communicate what was done, to transform the data into scientific results. It's hard, and I will say no one's going to laugh at your code. I don't know why, but mathematicians, because I've spent a lot of time in math departments, and mathematicians have this fear, oh, I can't share the code. I can't because people will laugh at me. That's just totally not what's going on. Like I've never seen that happen before. So try. I mean, if you are a software engineer, you know how hard it is, right? You don't laugh at other people who struggle with this. But nowadays you do have ChatGPT, so you can say, okay, ChatGPT, try to explain this code to me, right? Which is your own code. And if its explanation is wrong, then maybe your collaborators, your future stuff will also find that confusing. Okay, I've only got a few minutes left, so I'll go very quickly through what I call the up to standard and above in terms of reproducibility. That's making sure that others can run your code. So they can download it, they can read it, understand it. Can they run it? So first step is if they've downloaded your code and data, then how do they know what to do, basically? So I've got two projects here that I'm working on right now. So these are my own ones that I can make fun of. But say here is a project when my honors student, very talented honors student, and we've got our code on GitHub. But say a stranger comes along, there's all these different notebooks and Python files. What do you do first? Is the first step to run this analyze YT, to run the generate yield tables or the hazard generation file? I mean, it's totally not obvious, but here, this is why we have this README file. And if you look down, it says, okay, instructions. This is the order you should be running things in. This is what the data is about. This is the input and outputs for each file. And so that's one way. Another way I'm organizing it now is literally just to number all the notebooks. 0, 1, 2, 3, 4, 5. Make it super obvious. This is what the order that's important. Another one to keep track of is if you're using Mathematica, MATLAB, SAS, Data, any of these tools that you're getting for free at UNSW, remember that they are super expensive. And if you move to a different institution, you lose your license and you won't have access to your own, be able to run your own code anymore. I didn't think this was a big deal until I went to Europe, right? Just to tell you one last story. I went to a university in Lyon and I tried to ask to get Microsoft Word and PowerPoint installed, for example, just basic stuff for my computer. And the colleague in the office next to me is like, oh, okay, here's the USB stick of our pirated version of Word and PowerPoint and Excel, right? We all use this one. I'm like, are you joking? This is a top university in France, and you don't even have these basic things, let alone MATLAB, which is expensive, and so on. So try to avoid these kind of tools if you can, using free and open source ones. And if your data can't be shared, try to find some ways that you can share maybe a sample of it or illustrative data that reflects the patterns, well, some of the patterns maybe. So in terms of the specific, keeping track of which versions of packages are installed, if you're an R user, RM does this for you. So this is a very simple to use package. I'll let you to look that one up. But when you're writing a package, writing your code, you use tinyverse and you use span and you use some other packages. They change over time, right? So you need to keep track of what number you were using. And Python has its own versions in Conda, for example, or pip. Okay, so just a couple more minutes. Sorry to keep you over time. So going from 4 to 5, 4 is up to this point, we're talking about one research paper. Can I reproduce the results in that one research paper? 5, which is going beyond reproducibility, that's trying to help people to use your methods in their scenario. So this is talking about writing software, which I found a quote for. The benefits of code sharing focuses on potentially repurposing the code for other applications, but it's important to reiterate that the code's primary purpose is to communicate what was done. Code is not equivalent to software. Software is code that is designed and organized specifically for use by others in a wide variety of scenarios. And so this is a little photo of me 8 years ago when I was in my PhD days. I should have been on holiday. So here I was on a train, on a Shinkansen fast train in Japan on a skiing holiday, but I thought we had to finish this paper on time. So when we were going from A to B, that little blurry photo of me finishing some software package on the computer when we're on this holiday. And this package, we put it online as part of the paper, and I really didn't know what to expect from it. And soon afterwards, a total stranger down in Melbourne wrote his whole master's thesis repurposing my package. Right, I was doing something on variable annuities. He did some modeling on Bitcoin arrival rates, propagation of in use in the Bitcoin blockchain, which I found totally fascinating. And also, the same package was picked up by a research student in Iran who wrote his first research paper on the same software package, who ended up coming to UNSW as a PhD student, ended up being my PhD student. So Hussein used the same package that I wrote. And I had no idea that any of this would happen. Just put in a bit of extra work, put it out in the world, and then if it's packaged up as a paper, people start seeing, oh, this is this is reliable, I'm going to use this. And people download them a lot too, which is very handy, right? So 10,000 times my packages have been downloaded. But there is a cost to that. It does take a lot of non-negligible costs associated with development and support. But I'll sort of finish up on this last quote. Sharing research code that is poorly designed and inefficient is far preferable to not sharing code at all. Okay, so this is the last slide. Going forward, what do I recommend to you? Try to pick up one technique that I've looked at today, a reproducibility practice, and try to implement that for your next project. I mean, it might be a bit much to do it all in one hit. Try to just pick one. If your students are here, then I would say try to reproduce the results in the paper that's most fundamental to your thesis. You're basing most of your work probably on one or two papers that you're extending. Try to reproduce it. Otherwise, if you can't do that, you're in trouble. Supervisors, well, there's only one of you here. Try to get your students to reproduce the results of other people's work as part of their thesis. And finally, remember, ChatGPT is here to help. So thanks very much for your attention. And any questions, happy to take.
So is there any mechanism to recognize if you upload your code online and then downloaded by many people? So sometimes, because if someone cites your paper, then you get a credit of their citation increases.
Yeah. So if you upload some code to GitHub, there's typically no way to tell how many people download it. But if you make a software package, they usually keep track of how many people download the packages. And I think it's a huge difference. A software package that has like a level of respectability to it. And that's how I know that I would download it 10,000 at least times. And I can use that number when I go to job interviews, when I go to promotion interviews. So I definitely tell all those people that my stuff is downloaded 10,000 times. Another thing is, though, when you make your GitHub page, you put a thing here saying, okay, here is the BibTeX for the relevant paper. If you're using this code, please cite this as well. And so you can get citations for the paper that way.
Now let's thank Patrick for the interesting and insightful talk. Right, so here is the end of today's guest lecture, and thank you for coming, and we will see you in 7 and 8. Thank you. Enjoy.